And I say hello and welcome everybody. It's so nice to have you all here. We have a full room today. My name is Sven. I'm in the role of the moderator today. And as such, it's my job to do some housekeeping first before we jump into the actual talk. So, as many of you already know, and those who joined in for the first time will experience throughout the next 1.5 hours, we are aiming for interaction and sharing experiences here in our software intelligence talks. So if you have questions, own experiences, thoughts, doubts that you can, want, and are allowed to share with us, please feel free to do so anytime in the chat. I'm going to have a look at that. And I also have Jonas here with me in the background. We'll be giving our best to answer your questions in the chat directly and also forward them to our speakers so we can have discussions on audio here. In addition, we'll also have time in between the parts of the presentation here for some discussion on the audio and additional time in the end. So we'll have plenty of opportunity here for also discussing and sharing experiences. The questions don't have to be fully formulated, print ready. Just shoot whatever you have in mind. And if you feel more comfortable asking your questions in German, that's also fine. We can translate. For any other languages, we probably have to ask some AI to translate, and then we're all in for some funny experience probably. Yeah, so final thing, if you have any questions that you don't want to ask in front of the big audience, we also have time in the end, or we can follow up. Just give us a ping here, and we're happy to go into the discussion in detail and in private then afterwards. Final thing, from the organizational part, we would appreciate some feedback also on our format here. So we're going to start a poll in this Zoom session at the end. And I would very much appreciate if you give us some feedback, whether this was worth your while and what you took from the event. And also, if you leave the session, there will be a survey opening in your browser where you can give us some free text feedback, which is always very valuable for us. So we would highly appreciate that as well. And yeah, that's it from the organizational part. I'm going to jump over to a quick introduction of who we actually are and why we're conducting these talks. Many of us know us already. We are CQSE, a company dedicated to the topic of software quality for a little more than 17 years by now. We originally founded in Munich, Germany, but as you can see, we're spreading all over the place these days, including the US. So wherever you're sitting, from wherever you're joining, it's pretty likely that some of us is sitting near you and can support you if you want so. We're building the tool Teamscale, a software quality platform that helps you improve the quality of your software system. And one such topic we're discussing here a lot is our test gap analysis, which is going to be the topic of today's talk. I guess I don't have to say much about that. Attaching a price tag to bugs is a question, a challenge that many of us are facing in our day-to-day work. So I'm very happy that we have Florian Wartenberg here today, who's the submodule owner quality and testing at the Turbine Control Center of Vestas, to tell us a little about how they at Vestas managed to attach such a price tag to bugs. And together with him, we have Fabian Streitel here from our own ranks on the stage. He's the lead of our test intelligence team and supervises all the people working with test analysis and test process improvement. So welcome to you too. Very glad to have you here today on stage to talk about a topic that's obviously interesting for very many people. As we can see here, I just took the liberty to put all the logos here of the companies represented in today's talk. So that shows this is a challenge everybody's facing throughout industries, throughout technical domains, throughout different development processes. And therefore, I don't want to keep us from the actual content any longer. And hand over the mic to you, Fabian, for the first part. Take it away.
Thank you very much. All right. Thanks everybody for joining. Raising money for our testing process to improve something in our testing process is a really hard problem. Why? Because while the costs of testing are easy to measure, the benefits are not. After all, if you prevent one bug from reaching the end user, how much money did you save the company? It's a really hard question to answer. Today, we'll show you how Florian and I still managed to answer that for an improvement that we made at Vestas, namely test gap analysis. And hopefully that will also give you a good starting point if you want to do a return of investment analysis for something that you want to improve in your testing process. Now, we met Florian at Eurostar 2024, the conference, where we presented this test gap analysis. And test gap analysis helps you prevent production defects by identifying critical untested code changes. So code that went into a release that was changed, but you never executed it during any of your test stages. And the analysis allows you to adjust your testing behavior, your testing strategy to specifically target these untested code changes with additional tests and thus catch those bugs. Now, today in our talk, Florian will first talk a little bit about Vestas and why they were interested in test gap analysis. Then I will show how it works and what the research is behind it. And then finally, we'll show you how we did this return of investment analysis to convince Florian's boss to put up the money so we could implement it at Vestas. And then in the very end, Florian will show you how they're using it today. But before we jump into all of this, a little about the two of us. If my PowerPoint lets me click. Okay. My name is Fabian Streitel. Sven already said I lead the team called Test Intelligence. So my job is to find new ways to make testing easier, more effective, and more efficient with research. So that means we supervise a lot of bachelor master theses together with different universities in Germany. And out of that comes a lot of cool ideas what we could be doing to make testing more efficient. But unfortunately, a lot of the things that look good in a research paper don't naturally translate to practical application. So maybe the research is relying on some data that we can't get in an industry context, or is making some assumptions that we can't fulfill in a real practical project. So my goal is also to always bring these research results into practice, which is why we implement all of these results in an industry context with real projects to see if they actually have an impact in practice. And test gap analysis has passed both of these tests. So we have excellent research results that I'll show later on, but we've also implemented it with dozens of our customers in different industries and different contexts. Florian, I'll hand over to you.
So thank you, Fabian. My name is Florian Wartenberg. I'm working at Vestas as a submodule owner for quality and testing in our turbine control software, as Sven introduced me. I am from Berlin, Germany, but I live in Denmark for the last 7.5 years. I have been in software testing for, as you can see on my CV, for a little bit more than 15 years. I already specialized in that field during my studies for computer science in Berlin, and I have worked in different industries and different companies along software mostly in embedded products. And today I'm at Vestas and want to tell you a little bit about our history and why this important topic is valuable for our company and probably also for many other companies in similar situations. So I will tell you a little bit about our products, and the evolution of wind turbines has been over the last 150 years or so, from fully automatic wind turbines which produced around 12 kilowatts to today. And this is a picture of our newest and biggest offshore turbine with a 236 meter rotor diameter and producing 15 megawatt and potentially power for 20,000 households. So in this industry, but also in other industries, there has been one mantra for many years, and this has been bigger and bigger. And that also means that with the introduction of electricity, electronics, and also software, of course, that the products have become more and more complex. This massive rise in complexity, of course, also means that we have way more modules, sub-modules, and elements in our products. We have a lot of more interfaces. We have more and more software controlling stuff in our products, and of course, also there's a higher push and need for frequency of releases. There's many other factors, but of course, all of these mean that there is also a potential for errors that is increased. This is a graphic that I usually use when I'm a guest lecturer at the university in Aalborg, where I'm giving a lecture on this topic twice a year, to also illustrate a little bit to the students where we come from. I think this is mostly obvious to all of you, but also just to, in a fun way, illustrate a little bit the problem and where we come from. So this graphic is called the error ecosystem, and it is supposed to illustrate, even though this is not a industrial or software related picture, why issues and errors can happen, and how complex some of these issues are. So we have often different difficult environmental conditions. This is especially true in our industry, where we have to deal with a lot of environmental factors that are difficult to simulate. We have often unpredictable partners. We have sometimes or often the wrong strategy. We use bad equipment. We have unforeseen problems that occur that we did not calculate into the picture in the beginning. And sometimes or often we also have limited knowledge of the problem. So error ecosystem is something that always plays a role also when we develop software for our products. Another thing that is important to remember is that we also small and tiny issues that are development aspects that might not be relevant can lead to actually big and catastrophic issues. So an important message that I also want to convey is that everybody and every line of code has impact to the quality, and quality needs to be built in order to deliver successfully and good products to customers. If this is not the case, flawed software will hurt profits, and I have a couple of famous examples here that some of you might be aware of. It will be exploited. Again, some famous examples you might have heard of, or it, in the worst case, will hurt people. Again, some famous examples here where tiny things led to catastrophic impacts. So this being said, we know, okay, we have to quality assure, we have to verify, validate, and also as part of this, as one of the most important methods and techniques, test our products, and that usually is done in a layered structure where we have multiple test layers from unit over integration to system, and that also means that these layers have different purposes and complement each other. But still, it can be that if we are not doing it properly, that we have actual gaps where one of these layers is not catching an issue, and it actually goes through and is in the final product at the customer. So this is also called the Swiss cheese model. It comes actually from medicine and has been adopted also to this field, as it really good illustrates that these layers are complementary to each other, and the purpose of testing is important to have multiple layers of defense. But the holes here in the cheese actually illustrate that we have a test gap that goes from through all the layers and is in the final product. I have made an illustration here where basically, again, you can see these layers, and in the top you have a couple of developers that are creating some code, and we can see we have multiple layers of defense and where we are doing some testing, but we're actually not really good at it. We catch way too many issues too late, and still a lot of issues make it through to the customer. I think this is problems that many of you can relate to. So what we actually want to do is we want to, is it changing? Yes, we want to improve our test design and test selection to arrest some of these defects upstream. So you can see now when I click this picture improves over time. And we also want to enhance our code quality to reduce defect leakage downstream. In the end, what it comes down to is, in simple words, and it is simpler said as done, is we want to do less mistakes, and we want to contain as many as early as possible, and we want to catch them as early as possible, right? So now we're close to an ideal picture where we basically have a green line where we, by design and by doing strong architecture and requirements, catching a lot of issues already. And then obviously we have strong defense layers where most of the issues are caught as early as possible, and ideally rarely or no issues are leaked through to production. And one of these techniques that can help to get closer to this ideal picture is the test gap analysis, to take this hole in the cheese that I showed, to catch those and prevent those, and transition to a picture like this where you have a strong defense layer and protect your product from being a lot of issues that lead to the production. And with that, I give the word back to Fabian, who will now go in depth with the test gap analysis.
Thank you, Florian. Now, many of us are in this situation. We already have multiple layers of cheese, so to speak, but still too many holes in them. So too many bugs reach the end user. And then the question is always, why do we have this? Where are these bugs hiding? And that is a question that has also been asked a lot in computer science research. There's a field called defect prediction that aims to predict where bugs are in a software system. So you give me any software system and I try to make as good a prediction as possible to tell you where the bugs are hiding. And of course, the better we can do this, the more targeted we can be with our testing and the more holes in the cheese we can close. So there has been decades of research on defect prediction with hundreds of different papers on it. The one big result from all of that research is that for long-lived software systems, most bugs are hiding where we recently made changes. And now all of you are going to laugh and going to say, I already knew that. Anybody who does risk-based testing probably has recent code changes as one of the major risk factors, right? If you change code, there's a risk that you add more bugs. And so we all try to do already as comprehensive a test of our recent code changes as we can. But unfortunately, in practice, it doesn't work so well. Otherwise, we wouldn't be asking that question, why do we have too many production defects? And the question is why? And to illustrate that, I'll talk a little bit about how most of my customers decide what is a comprehensive test of all the recent changes. And that works by looking into these tools here. So our issue trackers, be it Jira, Azure DevOps, or something else. In the end, these record for a certain release which kinds of changes were done to the software. Features, bug fixes, maintenance efforts, and so on. And then we can go through those tickets and for each decide what would be a comprehensive test of all those changes. And that is the right idea to mitigate the risk that comes from those changes. But unfortunately, it has one really big problem in practice, namely that the information in these systems is incomplete. So there is a lot more happening on the level of code lines than is documented in these issue trackers, or even that is in our heads if we ourselves did the changes. So there is a lot of potential to miss testing critical changes simply because the people writing the tests or doing the tests don't know about them. And that is all sort of war stories at the moment. We wanted to know how much is that in practice. So we did a big study with one of our customers, Munich Re, a big insurance company in Munich, where we looked at one C# system, about 1 million lines of code for 2 releases. And for both of those releases, we determined which parts of the code were changed, this is the right bubble, and which parts of the code were executed during all of the different test stages, this is the left bubble. So everything from unit tests over automated integration and system tests up until manual end-to-end tests. And then, of course, we can overlap these and we can find out how many untested changes were there in the system. And the surprising part of this study was, the surprising result of that study was that after they changed about 15% of the code for both releases, over half of those changes went to production completely untested, even though they have a very structured testing process. So they do exactly everything I showed before. Someone goes through every single ticket in their issue tracker for every release and decides what would be a comprehensive test of all those changes and on which test level do we want to do the test. And still over half of those changes make it into production completely untested without anybody noticing. The second part of the study yielded another result, which was less surprising, that just confirmed our intuition. We basically looked at all the defects reported by the end users of those two releases, so the production defects, and traced them back to the line of code that caused the problem. And then checked, is that line of code in the untested code changes or not? And it turns out to be 5 times more likely that an untested code change caused a production defect than any other part of the software system. So not only are we unintentionally shipping a lot of code to production completely untested, it's also causing the majority of production defects. Or if you turn it around, wouldn't it be much nicer if we knew where these untested code changes are while we're still testing? Because then we could specifically target them and mitigate the risk that for those bugs that are still in there. Now you could say maybe at Munich Re that was an outlier, but unfortunately we've seen the same pattern over and over again in all different kinds of industries and all different kinds of companies. So this is another case study that we did with Allianz, where we saw over 2.5 months of measurement, still over 50% of test gap. So I would claim that having more than half of the code changes untested is even industry standard. It's not an outlier. So what can we do? The idea of test gap analysis is to give you this transparency about the untested code changes so that you can react. So we monitor on the one hand all of the code changes that are being made by looking at the version control system. This records every single line of code that was changed that went into a certain release. And on the other hand, we look at the execution information. That means we install so-called coverage profilers on your different test environments, from unit tests over automated end-to-end tests up until manual end-to-end test environments. And those measure sort of like some sort of monitoring for your application. Whenever anything happens with the application, which lines of code are getting executed. And then we know exactly where these untested code changes are, the code that we changed but never executed in any of these test stages. To show you what that looks like, I need a visualization. And if you've been in one of our talks before, you probably know this part, but I know there are some people here that haven't been in one of our talks yet, so I'll quickly explain it. This is a so-called tree map. It represents one software system, in this case, 1 million lines of C# code. So every rectangle you can see here in white is one component of the software system. And what I can do now is I can step into these components and draw all of the classes into each component. These are the black rectangles now. And then into each class, I can draw all of the different methods. And still, the more lines of code in a method, the bigger the rectangle. And now I have the whole executable code of that software system in this picture, and I can use color to show what we know about the code changes and the test coverage. So let's start with code changes from the version control system. If a line of code was newly added since the last release, if a method was newly added since the last release, then it's colored in red here. And if it was already there in the last release but modified, then it's orange. And if it wasn't changed at all, then it's still gray. So now we know roughly where the code changes were for this release. And then we can do the same thing with all the execution information. So all the gray code was not executed during any of the test stages for this software system. And all of the green code was executed in at least one of those test stages. And that works for both manual and automated tests, because these coverage profilers that we use to do this measurement, they don't really care how you execute the code, whether a tester clicks a button or an automated tool clicks the button or a unit test is calling the code directly. It just measures which lines of code are getting executed. And then we can put this together, sort of overlay it. And that gives us the untested code changes. And I'll quickly explain the colors. Everything that is gray has not been changed since the last release. And it's gray regardless of whether it was executed during the tests or not. Because this is the code where production defect probability is 5 times lower. This is not so interesting for our analysis at the moment. We care about all the colorful code, because there we made changes, so the risk for defects is high. And only when the latest version of a method was executed during one of our test stages, then it turns green. Or in other words, everything that is still red and orange, that is code that we changed but never executed. These are the test gaps, and this is what we want to focus on here. This is where the risk for production defect is highest, and where we would like to specifically understand what was changed here, what is the risk behind that, and do we maybe want additional test cases to mitigate that risk.
Bobby, let me chime in here, because we have some questions in the chat, and I think this is a good point to discuss that. I think you repeated it just now, but just to make sure here, what do we count as tested here? So what needs to happen for something to turn green on this picture?
The method needs to be executed at least once. So that means you need to have one test case that causes this method to execute. We don't care about how many code lines are being executed. So worst case, just a single line of code is executed, then this turns green. So we really know less about the green methods than about the red and orange methods, right? Because for the green methods, we just know they were executed, but we don't really know how well tested they were. But for the red and orange methods, we know that they were definitely not well tested, because they were not tested at all. So never executed at all, which is why we focus on the red and orange parts and not on the green parts.
Okay, and not tested here on this particular picture means it's not tested across any of the test stages, right? So exactly. From unit test to, I don't know, end-to-end test or acceptance test, there was not a single test going through.
Exactly.
Okay. In your experience, is in these projects code coverage not being used as a metric? So is the code pushed untested deliberately, or is due to timing constraints, or what are reasons for this to happen?
Usually what I see is that code coverage is employed, but only for the unit tests. So the really lowest test level. Or the higher test level, which in my experience are usually the ones that find the most interesting bugs, not the unit tests. Those usually don't have code coverage measurements when we first come in contact with our customers. And this is something that we help them set up so they can get this visibility here. And then, of course, the major benefit also comes from correlating that code coverage with the code changes. Because it's less interesting that the gray areas here were covered or not. Of course, that's also something you can look at. But the most interesting part is whether the changes were covered or not, because those really have the most risk for bugs.
Follow-up question popping in the chat. What if I still have some open bugs, some remaining bugs in the unchanged part of my code base? So does that mean we're not looking at that at all?
It's not the focus of this analysis. Of course, you can use the previous picture that I showed. Wait a second. PowerPoint doesn't let me switch. Here we go. You can use this picture to figure out if there are any gaps in your total coverage, right? So this just shows you, was any of the code at all executed or not? And then if you have large components like this down here that have no coverage at all, that could also be an indication that maybe there are still some bugs hiding in there because your tests are currently not at all looking at this code.
Makes sense. Maybe one more question, because there's been some discussion that even for the parts that are covered, where we have code coverage, we cannot really say that much, because coverage is, a relatively bad measure of the quality of how something is tested. Do you have experience with any other measures? The term is objective coverage methodologies here. So anything beyond code coverage that we can use to judge how good how well something has been tested?
There is a lot of research on this with different techniques. I think the one used most prominently is mutation testing, where we use automated tools to modify the source code of the application to inject bugs on purpose, and then check if the test suite finds them. And then you can see if certain methods, you can inject lots of bugs in them, but those are never found, then most likely that method is not tested very well. I think all of these methods are not really practically applicable for large software systems because they take a lot of time to produce results, because you need to run your test suite over and over. And if your test suite takes an hour, 2 hours, then you can imagine if you want to check 1,000 methods for injecting bugs, how long that will take. So unfortunately, there's no really practically much better methods. Maybe for smaller software systems, if you have a few thousand lines of code instead of a few tens of thousands lines of code, then that can be a viable solution, but for bigger systems, usually not.
Okay, so something like mutation testing is not part of what you're currently showing us here.
No, because unfortunately, it just doesn't scale.
Okay, so with improving here the green parts, or how well the green parts have been tested, but you're focusing on what's missing.
Exactly. Of course, you can sort of also improve the green parts by looking at which test stages are actually testing a method. And maybe you then find out, okay, the end-to-end test stage is not testing that method. Maybe I want the test for that. So that can be one measure to take here, because we can get this picture not just for the aggregation of all the different test stages, but of course also for each test stage separately to see the gaps for each of those test stages. So if you remember the cheese model, sort of see the holes in each of the cheese layers.
Maybe just to complement what Fabian said, right? I think all of us know that code coverage is not a qualitative measure of your tests, right? And we also all know that you can theoretically achieve 100% code coverage with bullshit tests. We all know that, right? But still, it can give you a lot of information and indication, especially if you assume that your test cases are written in a proper way, right? And I want to highlight that the idea here is that you figure out what's actually not tested. And I think if you're not testing it at all, then there is a high likelihood for you not being aware of how good is this component actually performing and introducing something to your final product, right? So it's still a lot of information and a lot of use that you get out of this here. Plus, I also want to say that we have been working with CQSE on requesting, let's say, also some guidance and help on which test gaps to prioritize on, right? Because if you have, like us, gigantic code base, then there might be actually a lot of these gaps which are difficult to look at in a prioritized way, right? So and there's also already research that they did where they can also basically also give a little bit of guidance on which of these most likely are a little bit more critical than others, right? And then you can look into it and assess it, and from that point of view, you can already find a lot of issues by systematically evaluating those, right? So of course, there is a grain of salt because it's not a qualitative measure of your test, but I think there is a lot of value and information in what is shown here, and you can utilize it a lot.
Okay, thank you very much for the addition. So there's some ongoing discussion about different possibilities how to interpret coverage. Maybe we can come back to that later. For now, I would say let's continue.
All right. Okay. Then I will talk a little bit about how you use this analysis. So imagine you get this picture for your own software system. What will you do with it? The idea is we set up this top part here, the data gathering part, fully automatically, so that whenever you're ready in your testing process to look at the test gaps, you can do so. So usually the idea is you do your tests like you normally would, and then after a while you look at the results and check if there are any unexpected gaps. And usually that means that you need some collaboration of developers and testers, because the developers know exactly what they changed and why they changed it, and the testers know which tests already ran. and what should be tested. And then together you can figure out which of the gaps are actually a problem. And then for those problems, you probably want to add additional test cases or change the strategy for the remaining testing phase. And then when you execute those test cases, that automatically generates new test coverage data, which is then automatically gathered and shown to you here. So then you have this nice feedback loop that you can run around in, where you do some tests, check the results. If you're not happy, adjust your testing behavior, do some more tests until you're happy with the result and ready to release. That's the idea. Now I have two caveats. We already touched on this with the question a little bit, but I want to be really clear on that. Number one, the goal of the analysis is not to have 100% change coverage in the end. So the goal is not to have the whole picture green in the end, because usually there are a lot of changes that are not worthy to have specific tests for that. So think of things like changing the button color from blue to green. If that didn't work, then probably that's not a big deal. And having a specific test for that kind of change would probably be a waste of time. And usually since testing processes are getting compressed more and more to have faster release cycles, we usually don't even have time to do comprehensive test of every single change. So the goal is always to give you this transparency and make it possible for you to make these risk-based decisions on where do we actually need to have tests and where can we get away with not having tests, to really find the spots where the risk for bugs is highest. And even if we had everything green, if we had 100% change coverage, as we already touched on, of course, that would not mean that there are no bugs. With testing, we can only ever show that there are bugs. We can never prove that there are no more bugs. And of course, that doesn't change if we now have better visibility into what our tests are actually doing. But the reverse is still as simple as true. All the red and orange areas, if there are bugs in there, we cannot have found them. So it makes sense to know where those are and then decide what to do with them. Now, this big picture is great if you're responsible for the whole release and the whole software, and you want to know if there are any major gaps left. But it's not so practical if you're a single tester working, for example, to test one user story. Then you would now have to pick out all the different methods that belong to that user story, and that would be a lot of work. Which is why in our tool Teamscale, we also break down this big picture into lots of smaller ones by taking data from your issue tracker, so Jira, Azure DevOps, or whatever you have, and then breaking that picture down to all those different user stories, bugs and defects, and so on. So every line here is one ticket from the issue tracker, and on the right, you can see how well tested the code that was changed for that ticket already is. And if I zoom into one of those, you see on the left in our tool the meta information from the issue tracker. So who worked on it in development, what's the title, what's the description, what's the priority, and so on. And on the right side, you see now, again, a tree map, but not the really big whole system tree map, but just the code, those methods that were modified when this feature was implemented in development. And that is a much smaller scope, and it all relates to this particular user story. So I can do my tests as a tester as I normally would, then afterwards check in here. And if there are still any gaps and I can't make any sense of them, then I know exactly who to talk to, namely the developer who implemented this ticket. So that makes it really easy to work on this with this information on a day-by-day basis and keep improving the coverage of these changes as we go through our sprints. And it also makes it really easy for test and development to work together because it's always focused on specific user stories and you always have a single person to contact in the other team. So that really is how most of our customers are using the analysis. Of course, that doesn't just work for the issue tracker, that also works for pull requests. So if you're working less with something like Jira and more with something like Bitbucket, GitHub, GitLab, and so on, where you have pull requests, then this is also a collection of changes that we can do the analysis on, and then we can show in the pull requests how many test gaps there still are and which methods are still affected. And that lets, for example, developers that write tests quickly see where they still have something to do. All right. That concludes the explanation of how the analysis works and the research results behind it. Before we jump to the return on investment analysis, Sven, are there any more questions that came up?
No, actually none in the chat that I can see. But maybe if there's some more question in your head at this point, feel free to just switch on the microphone and pick up.
Doesn't look like it.
I see in the chat, I don't want to ask, I want to see more of the good content. So I think that's asking you to continue.
All right, will do. Thank you very much. Okay, so now we've seen how it works, but of course, how it works doesn't tell us how well it works. And that was actually the question from Florian's manager when we presented this analysis to him. Is it really worth our time, our money, and the effort that we put into implementing this in the end? So do we really save more money than we invest in it? And we wanted to answer that question. And to that end, we did a return on investment analysis. So we calculated how much would it cost Vestas and then compared this to what the benefits are. And the benefits here for this analysis is, of course, mainly that in the end, you have less production defects. And that makes it really hard to measure the impact because we're trying to measure something that never happens, right? These production defects don't come to life, they don't reach the end user. And thus, how do you measure this? So what we did is we thought about a simple model, how we can model how this analysis impacts how many bugs we find in our testing process. And I'm going to walk you step by step through that model and then fill it with live with the numbers that we had measured at Vestas. Now, the model that we chose is really simple. It's basically that a test is like a filter on bugs. So before the testing phase, you have a software system at the top that has a bunch of bugs in it. Then you run it through your tests. And then hopefully afterwards, you have a software system with less bugs in it because you found some of these bugs. And with that model in mind, we can now think what happens with our code changes that we did for a certain release. Those fall into one of two categories. Either those changed methods were in some fashion executed by our tests, then they are in the left part, those are the tested changes, or they are test gaps. So they were never executed during any of our test stages. What we can use this for is we can now think about where this filter applies. Because obviously, if we never executed that code, then all of the bugs that were in the right-hand side are still in the software system after our test, right? They just slip through our testing safety net. The filter effect really only applies on the left side, where we do actually execute those changes. And of course, the filter is never 100% effective. I don't think anybody has tests that are 100% effective and squash all the bugs, but we have a certain effectiveness, so some of the bugs are filtered out. And so if you have, for example, 50% effectiveness, then half of the bugs are being filtered out in the left part of those changes. On the right side, effectiveness is 0%. We're not finding any of those bugs. That's the model. Now we can think about what happens when we add test gap analysis to it. Because what are we doing? We now know where these test gaps are, so we're adjusting our testing behavior and specifically adding test cases to cover those gaps. So that means what happens is that some of these orange gaps now turn green. And that means the green part is growing and the orange part is shrinking. And that means that some of the bugs that were previously in orange are now in green. And to those, obviously, the effectiveness of our tests now start to apply. So we're going to find some of those bugs, sorry. And that way, the analysis helps to find more bugs. Now, the question is, of course, how many more specifically? And for that, we need this test effectiveness, and we need to know how many test gaps we have. But in the end, with this model, we show that investing in quality, in this case, implementing this analysis, means we have less bugs afterwards, and less bugs means more money. But of course, that statement in itself is not convincing enough for management. I think everybody knows what the question is that comes from management at that point. It's how much more money. So we really need to put some euro amount on it in the end, not just show in an abstract way that we will have less bugs. So we really want to know how many bugs less and how much do the bugs cost us. So we really need to put a price on what a single bug is costing Vestas. And that's what we did, and Florian will tell you how we did it.
Yeah, thank you, Fabian. So in the wind industry, and I acknowledge that it might be a little bit more difficult in other industries, but Fabian will allude to other potential opportunities after how we did it. It is, we as an OEM, we don't own the turbines. We produce them, we design them, and we service them, and sell them, but we don't own them. Usually, especially in the service contracts, we have contractual obligations to our customers where we guarantee availability. So when the wind blows, the turbine needs to produce. As simple as that, right? And if it doesn't, but it could have and should have, we need to compensate our customers. And this loss in production usually is linked to issues. Can be hardware related, can be mechanical related, but can also be software related. So we have a very good insights of what actually was the problem in the turbine, what stopped the turbine, and what was actually a problem. So there we have an actual price tag on it, because we know exactly what it costs if the turbine didn't run, and what we need to compensate our customers with. And then we also can trace these loss in production to actual bugs and issues in our software. And this is exactly what we use to put a price tag on the test gap analysis. So of course, we made some high level assumptions, but we made a model where we actually then could link an financial impact to preventing some of these issues and some of the lost production, which is due to software, to the test gap analysis.
Exactly. And that let us put really a price tag on a single bug. Of course, that's only like the minimum price that the bug costs Vestas, because there might be other factors, like if a lot of turbines are standing still, maybe that's reputation lost, maybe that's future revenue lost. So there are more costs to a bug, but those are much harder to measure. And in this return of investment analysis, we always try to do a conservative measurement of what the return of invest will be, so that we can always say, well, it could be better, but this is at least the minimum that we know, to have a really strong case to make, so that in the end, the improvement that we want to make to the testing process, in this case, test gap analysis, is approved. So we took only this lost production factor and did not, in this return of investment analysis, take any other kinds of monetary losses or more abstract losses into consideration. What we came out with was a number. Now, the real number that we measured is, of course, a trade secret for Vestas. So the number that we show here are sort of ballpark numbers. Please keep that in mind. So let's say one bug costs us 45,000 euros on average. And we also measured the other two numbers that we need. So we measured the test efficiency by looking at how many bugs were found during the different test stages and how many bugs were reported for the different releases in the past from the end users. Then you can get this test efficiency, how many bugs did we find in the test and how many did slip through. So that is also based on historic data, same as the cost of one bug. And then finally, we did a one-time measurement of the test coverage and the code changes for one release. And that gave us a test gap of ballpark 48%. So again, industry standard. And with these three numbers, we now know how many bugs are slipping through our testing net because of these test gaps. And now we can predict what happens when we add test gap analysis. And this is really the only part of this return on invest analysis where we can't rely on historic data, because we don't know what exactly will happen when we implement test gap analysis, because it depends on how well it's implemented, how well developers and testers work with it, and so on. So we have to make a prediction into the future. And to still have a strong case, we did not just make one sort of off-the-cuff estimate, but rather we did three different scenarios for how this could develop in the future if you add test gap analysis here, and based two of them on experiences that we had at other customers where we did have hard data about what happened after they used test gap analysis. And then one final one to have a really conservative estimate, to have a sort of baseline where we're sure this will definitely be achievable. Now, these are the three scenarios. you've already seen the two customer test cases, case studies. At Munich Re, you saw that they had over 50% test gap. And over the course of many years using test gap analysis and rolling it out to almost 100 applications, the worst test gap number that they have today is 10%. So they reduced their over 50% test gap down to 10% or less. So that was our most optimistic scenario. Allianz, a shorter time frame, in 1.5 years, they managed to reduce their test gap by 20 percentage points. So that was our sort of middle scenario. And then the really conservative scenario where we're sure we're definitely going to achieve this would be 8% less test gap. And I'll walk you through the scenarios, what happens in each and how much money is saved. So if you take the most conservative scenario and reduce test gaps by 8%, so from 48 to 40%, then we have about 8 production defects less times 45,000 euros. That's 360,000 euros. If you do the more advanced scenario and reduce it by 20 percentage points, that comes out at almost a little bit more than 1 million euros. And the most ambitious scenario, down to 10% test gap, would save almost 2 million euros. And so with these three scenarios, we sort of open an umbrella of possibilities, but with one very conservative sort of baseline. And those 360,000 euros were already more than the investment needed at Vestas to actually implement test gap analysis, way more. So that already was very convincing.
One question here at this point, because it just came up. Your kind of starting point was the 45,000 euros estimate of cost per bug. Can you briefly repeat where this number actually comes from? So how did you compute that?
Florian, do you want to take that?
I can do that, yes. So let's assume the turbine is not producing when it should be, and there's a production loss. There's an agreed amount of money that needs to be paid to the customer to compensate them because there is an availability guarantee. And those numbers we know. We know what are the liquidated damages that we pay every day, every year to our customers due to production loss. And obviously, because this is such an important thing, we have a lot of data and a lot of systems that help us to identify why these turbines were stopped. And some of those relate to software. And those we used based on the liquidated damages numbers that we could abstract from these production losses to calculate a number for what a bug costs. So, but the number that Fabian uses is not the real number because we don't want to share that, obviously. So it's a number that's to illustrate the calculation, right? But the way we get to the number is the real one, which I just shared.
So maybe as a metaphor, it's sort of like a service level agreement for your customers, right? If the wind turbine isn't running 90% of the time, then you pay them X amount of money. Correct?
Okay. Thanks for clarifying.
Yeah, it's energy prices, right? So what they would have produced, and then that is calculated what they would have produced and what I would have earned, and that needs to be one to one be compensated. And obviously this is super important because this comes directly out of the bottom line.
Mm-hmm. Okay. Maybe one follow-up question at this point, probably more in the direction of Fabian again. Now you showed us what's like the initial return on investment here.
Mm-hmm.
Is there diminishing returns to be expected? So along the way, if I'm going to continue to use something like test gap analysis, I will probably continue to have costs to use it. Will there be less value over time?
I would say no, because you're changing different parts of the software system each release, right? So there will be more gaps every release. Of course, it might be that the total number of gaps decreases a bit, but it will never fall to zero. So there will always be some returns. We did not measure this with anybody over the long term, how these numbers change and decrease. But if you stop using test gap analysis, it will build up again, right? Because then you don't know where these code changes are anymore. And then you're probably not very good at testing them anymore, same as you were before you had the analysis. So I would say that there might be a little bit of a diminishment, but not very much.
If I may add to this, right? And I think there are two parts to it. And I think one of them has no diminishing return and one of them has a diminishing return. And I will allude to it a little later when it's my turn again, but I think it fits in here. So I will take a couple of these things now. So we are using the tool and the test gap analysis for two things. One of them is to prevent introduction of new test gaps. This has no diminishing returns. This is the same value over and over again because you make changes, you make new code, and you want to have them ideally properly tested, right? Obviously, there are the limitations of coverage as a metric, but that we discussed already, and we can dive into it later if you want to. So, and then the second one is that you have a status. You have, let's say, this amount of gaps that you should close. So basically, we have frozen this picture because it's not possible to introduce new test gaps. And we're trying to address the existing gaps and close them. That has diminishing returns because you can only do that once. So this one is a one-off, which has a lot of value and helps you to improve your code base as a whole. And then there is the ongoing use in the CI/CD pipeline where basically there is no diminishing return. And I would argue that the number two alone justifies the cost, but number one, of course, has a lot of diminishing returns because it's a one-off, but of course also is a one-off with a lot of value.
Mm-hmm. And just to wrap up this, this where do the numbers come from thing is the question more or less in the chat that these are historic numbers you're using here as a baseline to predict what the future bugs might cost. So you're not really measuring anything that might happen in the future, but you're just using the historic data here and the monetary implications of those past bugs to estimate what future bugs might cost.
Mm-hmm. Correct.
Okay. Then there's some more questions regarding the other numbers here, actually. So can you explain maybe in a bit more detail how you calculated the number of bugs that you prevent using test gap analysis?
Mm-hmm. So does it mean the test efficiency here or the 8 less production defects here? Do you know, Sven?
Yeah. I'm guessing somehow probably both. Maybe you start with efficiency and then you map that to the saved percentages.
Okay, so I'll start with test efficiency. How do we know how many bugs our tests are finding when we run the tests? And that we know from historic data again. So we look at the number of bugs for a release found during the testing stage. Let's say that's 10. And then we look at the number of bugs that were reported by the end users for that release. Let's say that's also 10. Then you have 10 to 10. So 50% of the bugs were found during testing and the other 50% made it to the end user. That's how you get the test efficiency. So all you need is data about how many bugs do you find during testing and how many bugs do reach the end user for each release. And then you can do this for 1 or 2 releases and you get an average. Now to get how many production defects you get if you have a certain reduction in test gaps, that comes from the model that I showed before. This is what I showed here. If we know how many bugs are in those changes in total, those are the bugs that we found during testing and the bugs that reach the end user, right? Those are all of these up here. And we decrease the test gaps from 48% to 40%, for example, and we know how many bugs moved to the left and how many bugs more will be found because the test effectiveness now applies. So if I move 10 bugs to the left, 50% are being found because of test effectiveness, then that means I find 5 additional bugs. That's the calculation we do. I hope that made it a little clearer.
I hope so too. I think we covered all the questions in the chat. There's a lot going on right now, so I'll be reviewing the chat a little bit more And if there's more questions coming up, I'll hand them to you later.
All right. I'll try my hand on a quick summary how we did this return of investment calculation, because I think it generalizes to more types of improvements than just test gap analysis. If you want to make a return of investment analysis, you need a clear mental model of how the improvement that you want to make prevents bugs. That gives you a way to calculate exactly how many bugs you can save depending on how the improvement turns out. These are the different scenarios that we did. And I recommend you do more than one scenario because that is more convincing to management. And I recommend you have one very conservative scenario. And in this whole return of investment analysis, always try to be conservative. If you have to make assumptions, always try to make the most conservative assumption to strengthen your case and in the end have a convincing argument. And then the only thing left is to calculate this minimum cost of one bug. Again, minimum to be conservative, right? We don't need to have a comprehensive calculation of the cost of one bug. If the minimum cost already justifies our case, then larger costs will, of course, also justify our case. And of course, not everyone is in the wind industry, so not everyone has this nice lost production factor, but there are many other ways of calculating a minimum cost for one bug. Think of average time it takes developers to fix a bug and testers to test it. Then take that times their salary, and then you have a minimum cost of one bug on average. Or maybe you have a customer service team that is very important, and they have to calm down customers for high priority bugs. Maybe that way you can at least calculate a minimum cost for the high priority bugs, and maybe that already justifies the improvement that you want to make. Or maybe you need to go on site and service machines on site, or maybe you have SLAs where you pay penalties and so on. So there's a lot of different ways to calculate a minimum cost of one bug. Which one makes the most sense, of course, depends on your industry. Maybe in your industry, you can even put a price on opportunity costs. If we have less time, have to spend less time on bug fixing, maybe we can spend more time on new features, and that will give us X amount of money. I don't know. There's thousands of ways to calculate this. Try to find the most convincing number that you can measure the most accurately, because that gives you the strongest case. All right, then for the last part, Florian will tell us a little bit about how they're using test gap analysis today after we got it approved.
Yes, thank you, Fabian. And a couple of things I already alluded to, right? So we can see here on the screen the trend, the test gap trend, and you can see that we also have been reducing them over time, not linear, but of course it also depends when you have time and how much effort you can spend in reducing the gaps that are existing. But as I mentioned, we use it in a twofold way. We use it to have a clearer picture on duplication of tests, on test gaps in specific different test layers, the layers that we saw with the cheese. We use it to prevent introduction of new test gaps as Teamscale votes in our PRs and as part of our CI/CD pipeline. And then also what we do today is that it is an integral part of our quality metrics to have all teams actively evaluate the existing test gaps and prioritize them and make decisions on if there is potential risk and value in closing them. So I will not be here and say that all of these gaps need to be closed. I think that there is also some gaps which provide lower value, right? But as I said, we should do it on a risk-based manner, and we should evaluate the potential gap, right? And at first glance, this is just an information, and what we do with the information, that is up to us, right? We have decided that we want to evaluate the gaps and then, of course, decide which of those might be high risk and close them, and then also introduce a rule set in our pipeline that helps developers and prevents introduction from potential new gaps. This is what we do today, and I think right now, of course, all change processes are a little bit tricky. We all know this, especially in bigger companies, but I think developers are getting more and more fond of the tool, and also it gets more and more natural to have it as part of our daily work.
All right, that concludes our talk. Thank you all for participating. I'll hand back over to Sven for the wrap up and maybe more questions.
Yes, thanks a lot, you two, for diving with us, taking us with you in that journey and calculation of costs here for bugs, and how you estimated potential savings by improving the testing process. I think that was really interesting, judging from the discussions we have in the chat still ongoing. I think a lot of the participants found that interesting as well. There are a couple more questions that we have here. So some questions go into the direction of, or some discussion, additional cost points, like, for example, if you have to do a CC evaluation of the software before release, you have high costs for release. So the cost for the bug is overshadowed by the cost example for releases. So if you have such costing factors, probably would make sense to include it in a calculation for the return on risk, right?
Yes, definitely. If you need less bug fix releases, then that's cost saved in this case.
Okay, so you would probably, you were talking about doing conservative choices here. It would probably make sense then to just use the cost of releases and try to estimate how many releases you could save by catching the bugs more early.
Yeah, of course, it's hard to tell without the specifics, but if that's the strongest or best to measure factor, then I would use that.
Sounds good. There's one more question. I'm not sure I understand that. I pass it to you, and then we see if you can figure this out. Could you tell how do you do the selection? Which part is critical to test and which part is not? So is that manual checking or is that automated?
I'll try to answer it the way I understand it, and if it's not the right answer, if I'm not answering the right question, then maybe comment again. So I understand it this way. If you get these gaps, how do you know which of these gaps really to address and which ones you don't need to address? And in the end, that's not a decision that can be made only in an automated way, because any type of analysis tool, any automated judgment here, it doesn't know about your business, it doesn't know about the criticality of certain functionality, it doesn't know how end users react to certain changes and which ones are more critical or not. So we can use an automated way to make the final decision. So this is really, in the end, the analysis gives you the transparency where these things are, and then you make the judgment call which ones are the most risky. Of course, as Florian mentioned, we do have some research on can we make a good first estimate in an automated way, where we use data from about the complexity of the code change, about the criticality of the issue from the issue tracker, and the centrality of the method and so on, and lots of other available data about these methods to sort of make a prediction how likely it is that this is a critical code change. But in the end, you can't let just a machine make that decision. You need to look at it, and the prioritization that I just talked about, that just helps you sort of start with the most likely candidates and work through those. I hope that went in the right direction. Otherwise, comment in the chat.
I'll just chime in. One more question that goes into a different direction. So could you elaborate a little more on the system you have in place for calculating the prices? So is that something you do in the day-to-day practice when new bugs come in, or how do you go about this calculation? Is it some ongoing thing, or was this a one-time project to get to these numbers?
Florian, I would hand that to you.
Yes, so we have daily updated dashboards for that, right? Which tell us which issues cause which amount of money, right? But obviously the the calculation that we created, where we created some Excel sheets and so on, right? They are not updated regularly, because I know which issue costs which money, and I now have the tool, right? So obviously we can always revisit the calculation, and I can just update the numbers in the Excel, and I can also look into when we have reached the return on invest, right? But internally we have a lot of dashboards that show us the cost.
So because this loss penalty is such a central thing to you, that's something you're continuously calculating. But of course, the case study or the return on investment calculation for test cap analysis in particular is nothing you do in an ongoing way. But
Correct. Correct.
Okay.
Correct.
Okay. Are there more questions? I know there's one more question here in the chat, but I need to read that before I can actually give it to you. Are there more questions that you may even also ask on the audio? I know that many of your microphones are working from the beginning, so if there's more questions, just shoot, and I'll be reading the chat in the meantime.
I have one more question. So basically, you're looking into the history, how much bugs you find in which release, right? And you need to freeze numbers at any time. So at the very beginning, most likely your efficiency of a test will be 100% because your feedback is 0, right? So you need to decide, okay, now we freeze the numbers and calculate our test efficiency. Is there a certain method when you decide to freeze the numbers? For example, a burn up of bugs, for example, that it's like it's going in a certain graph or something like that, it comes to an end, and now we can decide, okay, we freeze the numbers.
We did not do it this way. I think we used a much simpler approach. We simply took multiple releases and then calculated the number. Okay. And then you can see that if those are sort of all similar, then it's very likely that sort of the average is a good enough number.
Okay.
So if you have the data into the past for a longer time, then you can just do that. I think that's the easiest way.
Yeah. Okay. Got it.
Okay, that actually saved me the time reading and figuring out the question, because that was the question I was just reading.
Feel free to ask more on the audio.
Yeah, there's one more question. If you have such kind of feedback on test gaps and things that are slipping through testing, how do you actually hand that to testers and developers? So how does the feedback get from this nice visualization to the people?
Mm-hmm. That's what I try to show here. This is not the graphic that testers and developers usually consume directly as single testers and single developers, maybe test managers if you're responsible for the whole release. But as a single person, I'm either interested in this is the user story, the defect report, whatever in Jira, for example, and I want to know if that is tested well because that's what I'm testing at the moment. Then this is the visualization. And then you have only very few gaps here that you need to analyze. And of course, in the tool, this is interactive, right? It's not just a picture. You can hover here, you can see the method name, you can see the diff for those changes. And of course, if as a tester, you're not close enough to the code to understand that, you can ask the developers about this. So that's really a very practical way of doing this. And the second way is to look at pull requests instead of issues. If you're more comfortable working with pull requests, then of course this is also just a set of changes where certain methods were changed, and we can see how many of those were already tested and how many weren't. And then this is also a very practical way because you have all the diff information there, what exactly changed, and you also have a single developer you can talk to for this diff.
But we also have the tree map dashboards inside the tool for all of our functional areas and for our global code and with all the features that Teamscale provides, right? Maybe also if you go back to the other picture with the one from Jira, Fabi, one thing that I wanted to highlight, because we had this code coverage discussion, right? So I do not have a judgment on how good the stuff that is green is. How good am I with my green stuff? I do not have any information about this. But I know that if it's yellow or red, it's high risk because I didn't do anything. So if I don't do anything, the probability is high that I do not catch anything. So, and that is also what the focus is. The focus is on the yellow and the red. And of course, I do not have any information on the green because I don't know how good the test cases are. And there, obviously, you need to implement other measures like mutation analysis, training, and of course, trust your developers and test engineers.
Okay, I think that's a very good final word here. Trust your people to do their job well. I don't think we have any more questions in the chat at this point, so I'm going to just grab the screen for me again, since I also see some people are already leaving, and I would highly appreciate to first of all say thank you to both of you, Florian, Fabian, for sharing your insights with us. Thank you very much for everybody and participating here for the discussions we had. I think that was really great, and there was a lot of activity in the chat and also on the audio here. We would appreciate a lot if you also give us feedback how you actually experienced that. Here we'll be starting a poll now. And as I said, you can also leave free text feedback in the survey that opens when you leave the Zoom session a little later. Final words here from my side. If you're now curious about test gap analysis and want to figure out the details of how that actually works and how you could get started with test gap analysis, we're going to talk about that in about 2 weeks. We'll put the link to the registration here in the chat in a second. So if you're curious to learn more about how you could actually get started in your particular context, what you need to get ready for using something like test gap analysis, then join us there and we'll dive deeper into the topic. And yeah, since I already see the first people leaving, I want to say thank you again to everybody. If you want to head out for lunch already, I'm not keeping you away from your well-deserved food. And if there's a couple more questions you have in mind, we are still here for a couple more minutes and can discuss those. For those leaving, thank you again. Goodbye. Have a nice day. See you soon again. And for those who want to stay, let's discuss more questions.